Okay, so this is the third lecture on Galilean transformations, and on this lecture we'll be going through the Michelson Morley experiment. Okay, now I just wanted to review a little bit before I talk about this Michelson Morley experiment. You remember, for classical mechanics, we said there was an infinite number of possible coordinate systems, all inertial coordinate systems, and we said it was impossible to detect any sort of absolute motion because they all were invariant to Newton's laws right here. And we had these Galilean transformations. Remember going from Frank to Mary. Remember, Mary is the prime and Frank is the unprime. So here's the positions, the times, the speeds, and so on. And was it going back in reverse? And we said you just change the prime and the unprime and change the sign of the V. And then we said the transformation was just going from this sort of a coordinate system to the red coordinate system where the T prime well, I should say the constant values of x, these are constant values of x, are now tilted a little bit right here. And then we said the slope of this was 1 over v right here. Okay, that was classical mechanics. Then we went into electromagnetism and we said, well, there only seemed to be one good coordinate system right here, which means that you can detect absolute motion right here. And we did it. We looked at two positive charges, and we said in Frank's frame these two were at rest, and we got this force, which is just Coulomb's force on that one right there. And then we ran over to Mary's frame, and we got this extra term right here. Very small extra term right here, because even if we take into account the motion of the Earth around the Sun, the Earth moves about that speed. If you plug that in, this extra term only contributes about that much right there. Right. So it looks like trying to find that one good coordinate system, the one where the speed of light is the speed of light, is going to be a difficult experiment. I didn't bring up that, remember, when we talk about electromagnetism, it's really Maxwell's equations that you work with in electromagnetism. I just wanted to write one of them out. You know, you go through Gauss's law and Faraday's law and so on. Here was Ampere's law. There's what you got for Ampere's law. The integral of B dot dl is mu naught I enclosed plus 1 over c squared, and the change in electric flux with respect to time. The only reason why I bring up this one is because it's the only one that has a speed in it right here. It's the only Maxwell's equation. And you notice that if we were to switch to another coordinate system where the speed changes using the Galilean transformation, we'd have to put a c minus v here, squared. And that's definitely a separate equation. So this equation, if you're going to say it works right here, then you're going to have to say this only works for one coordinate system, the coordinate system where the speed of light is the speed of light. And so I called that still space right here. Sometimes they call that the ether frame right here. And so what we want to know, we want to find out is how fast is the Earth moving through this ether frame right here. And so it's like a medium. It's just like sound requires air for sound to travel. And so for the wave to travel, the light needs the ether right here. And whatever that frame is, it's got to be quite thin or tenuous because the Earth has been revolving around the sun for billions of years and hasn't slowed it down. So it must be very thin, whatever that material is, and it has to be quite rigid, because the speed of light is very fast. If air were more rigid, sound would travel faster. It's like through water. Sound travels much faster through water because it's much more rigid. Speed of light is very fast, so this frame, this ether frame, or this still space frame, must be quite rigid right here. And so it was actually Michelson that determine this. I think I said before that this is probably one of the top physics experiments in all of science right here, and most profound right here. And so how did he do it? He was also an American. He was from Case Western Reserve, which is a university in Cleveland, Ohio, right here. Okay, so how did he try to do that? Remember, you're trying to look for things this accurate right there, which is, not easy to do right here. Okay, suppose we have a pond right here where the water is not moving, and the water will be our medium right here. We don't feel it, just like we don't feel still space right here. And let's say we have a swimmer that can swim at a speed c in this pond, exactly at a speed c. And he wants to know whether this pond is flowing or is it still. So what he does is he marks out a distance L perpendicular, two lengths perpendicular to each other. And then he starts here and he swims at a speed c this way. When he gets to the end, he swims back at a speed c. Over here, he swims up with a speed c and swims down. Now, if the water is completely still and he always swims at a speed c relative to still water, the time this way and the time this way should be the same right there. It's exactly the same time. But now, let's take the case where the still space is moving this way or the Earth is moving this way with respect to the still space. It's like a river right here. And you got the water moving this way. Now you come over here and you want to swim some distance L down, and you want to swim a distance L this way. Go there and back. Over here you go there and back. Now you always swim at a speed c, but if this is moving at a speed v, if the flow rate is a speed v, then your speed this way is actually c plus v right here. You're going downstream right here. And when you come back, you have to fight the river right here, so your speed backward is c minus v. Now, when you go across this way, you can't swim this way because the water will make you drift down and you'll end up over here someplace. So you've actually got to aim back this way right here at a speed c so that the v brings you right across. And so your speed actually this way, just from Pythagorean's theorem, is the square root of c squared minus v squared. So this is the speed you come. And on your way back, again, you've got to aim this way so the river brings you back. You come back and forth these two. And it just so happens that this coming back and forth this way and coming this way are not the same amount of time. And the bigger the v, the more the difference right here. And that's what we're going to use. That's what Michelson Morley Experiment used. He used to just measure the speed of light going back and forth this way and see if they're the same right here. So let me draw his experiment right here. I'm going to erase this since we probably don't need this anymore. So start out with some light source right here. So you have some light source. He used, let's say our wavelength of our light is, I think he used around 500 nanometers, monochromatic light. He used white light too, but we're going to use 500 nanometers, monochromatic, one wavelength light. So here comes the light out right here. We'll collimate it so it doesn't get all over the place right there. So all the light is going this way right there. Okay. Now out here, we're going to put a mirror 45 degrees, tilted 45 degrees, and it's half silvered. What I mean by half silvered, that means that half the light that hits it is going to reflect and half the light is going to transmit. So half the light is going to go up this way. And half the light, I need another color here, is going to move off this way, right there. Okay. And then what we'll do is we'll put a mirror on the far side, right here. So right here, we're going to put a mirror here. And over here, we'll put a mirror. Okay, so this is 100% mirror, so that blue light gets reflected straight back, right here, gets bent, comes straight back this way, again, hits this partial mirror, part of it gets reflected All I care about is the part that keeps going. And likewise, this one over here, this one that went this way right here, is going to come back. Again, part of it's going to go through, part of it's going to come down like that right here. Now, I can't make these two distances exactly the same length. It'd just be too hard right here. So I'm just going to call this length L1 right here. L1. And we'll call this length L2 right there. Okay, now when these two beams come toward each other, they're going to produce an interference pattern. And what I'm going to get is I'm going to get some bright and dark spots right here. Now I did an experiment with this laser. If you notice this laser right here, I taped a single hair on the laser right here. If we look at the laser right here, taped a hair on it. So that means when the light hit the hair, some of it went around this, diffracted around one way around the hair, light diffracted around the other, took two different paths, met on the wall, and produced a pattern like this. And I'll show you that pattern. Okay, you can see that pattern. There's dark and bright spots right there. Okay, so now you'll notice that the light shared this part of motion and this part, but the only thing that was different is this one went back and forth this way, this one went back and forth this way. And we already said that the speed, since we're assuming this, we'll assume the flow rate is this way, so we'll assume it's this way. This is the velocity of the medium, which means the Earth is moving through this way through still space. We know that the speed going in that direction will be c plus v, and we know the speed coming back will be c minus v. And just like we said before, the speed going up will be the square root of c squared minus v squared, square root of c squared minus v squared, and the speed coming down will be the same, c squared minus v squared. Okay. Again, we don't have to worry about this section or this section right here. So now I'm gonna label, I just want to label here an A, and I'll label C. That C is not the speed of light, this is the label C, and this is D up here, right there. So if I just wanted to, first of all, just look at the time from here to here, back to here again. Remember, since velocity is distance over time, the time is distance over velocity. So the time from A to C, back to A again, A to C, back to A again, is first the time it takes to get down. Remember, time is distance over speed. It's L1 over C plus V. L1 over C plus V, plus the time it takes to get back, which is also L1 over C minus V. L1 over C minus V, right there. And then I can get a common denominator right here, which is L1 times C minus V plus L1 times C plus V. All over C squared, all over C squared minus V squared. Okay, and then we can cancel out some terms. Here we get a L1C plus another L1C, that's 2 L1C. The L1V minus L1V plus L1V is gone, all over C squared minus V squared. Okay, so there is the time. I think what I'll do right here is, I think I'll pull out a C squared here. So this is 2L1C all over C squared, 1 minus v squared over c squared. 1 minus v squared over c squared. And then I could even cancel c right there. So this is 2L1 all over c times 1 minus v squared over c squared. V squared over c squared. Okay, so there is the time it takes to go down and back. Now the time it takes to go up this way and back, that's ADA. The time from A to D back to A. It's going to be L2 divided by that number right here. L2 all over the square root of c squared minus v squared. Plus the time it takes to come back, but it's the same time because the speed is the same, so I can just double this. Okay, and I think I'll pull out the c squared out of here also. If I pull the c squared out, it just becomes c, so this is 2L2 all over c times the square root of 1 minus v squared over c squared. 1 minus v squared over c squared. So you can, by comparing those two, the only difference between these two is this one has a square root here. This one over here doesn't have the square root right there. Okay. So now what do we want to do? Well, we want to just subtract these two because that's what gives me the interference pattern. Subtract the two times. So if we just say delta t is just TA, I'll pick ADA minus TACA. Now if I subtract these two right here, I get, well, what's common to both of them? I get a 2 over c. I'm taking this minus that right here. And so I end up with L2 all over the square root of 1 minus v squared over c squared minus L1 all over, without the square root, 1 minus v squared over c squared. Okay, so there is the difference in time right there. But I'm always going to see this interference pattern. That's not what I'm looking for right here. What I want to know is, suppose I rotated this whole thing 90 degrees. Now we're changing their two roles. Does this pattern change right here? That's what I'm looking for, the change right here. Now I don't have to rotate this. I can just wait 3 months because, you know, if here's the sun, here's the earth right here, and if you do it at midnight, you're right there. And then if you wait 3 months, you're over here, and now at midnight, you're right there. Well, now you've rotated 90 degrees. You could do that. This looks like an easy experiment. It's a very difficult experiment. You need to cut down the vibrations so much that, you know, just people walking around the building outside is enough vibration to mess up this signal right here. He had to put it on huge blocks of granite to keep the vibrations down. And if he wanted to rotate it, he put it on floating mercury so he could rotate the whole thing right here. So it was a very, very tough experiment right here. But now what I want to do is I want to rotate everything 90 degrees. What happens when I rotate this? We're going to get a different time. Let's put a little R, meaning now it's rotated right here. Now, the red curve will have the square root with it, and the blue curve won't have the square root with it. We're swapping the two right there. And so really all that's going to do over here to this picture right here is it means that this one doesn't have the square root and that one does. That's all we did. So this one's going to be 2 over c L2 all over 1 minus v squared over c squared minus, and that one will have the square root, L1 all over the square root of 1 minus v squared over c squared. Okay, so now what I wanted to do is I wanted to say is how much did it change between here and rotated 90 degrees? So So I need to take the difference of these two right here. I need to subtract these two to see if there's any sort of difference right here. So we'll take this and we'll subtract off that one. So delta TR minus delta T. So now we're going to subtract the two. Now they all have a 2 over C in it, so we're going to take this one and subtract off that one. Now, you notice if we look at this term, we're going to take this term and we're going to subtract out that term. Well, if you subtract a negative, that's going to be a positive. They both have the same denominator, so this is just going to be L1 plus L2. L1 plus L2 all over 1 minus V squared over C squared. And then we're going to take this one and subtract off this one right here. So here, if we subtract that off, we're going to subtract. So if we subtract these, we're going to take this minus that. So I'll pull the minus out because I'm subtracting that. That means this is a plus then. We would have L1 plus L2. L1 plus L2 all over the square root of 1 minus V squared over C squared. Okay, and now since they both have an L1 plus L2, I can factor that out too. So this becomes 2 over C. We pull out the L1 plus L2. Now I end up with 1 all over 1 minus V squared over C squared. Minus, and then you have the square root term. 1 all over the square root of 1 minus V squared over C squared. Okay, now we already know that V is nowhere near C. V is a very small, otherwise we would have noticed this before. So, you notice we have something on the order of 1 minus, we have, on both terms, we have 1 over 1 minus some small number, V squared over C squared, raised to some power. This is to the 1 power, that's to the half power. So this is to some power n, right there. Well, this right here is approximately, it's a little bit more than 1. It's actually 1 plus n epsilon. It's just the first two terms in the Taylor series right here. It's just that the next term has an epsilon squared, and for us, epsilon squared is insignificant right here. It'll just make the math a lot simpler right here. So that means this right here becomes 2 L1 plus L2 over C, 2 L1 plus L2 all over C. And then this term now, if we compare it, epsilon is V squared over C squared, and n is 1. So we end up with 1 plus n in this case was 1, and epsilon was V squared over C squared. So it's just V squared over C squared. And then we have minus. We get, again, it's just like that, except n is a half, because we got the square root here. So this is 1 plus V squared over 2C squared. There's the 1/2 right there. Okay, and then this, the 1's drop out, and the V squared over C squared minus a half of V squared over C squared is a half of V squared over C squared. So this is 2 L1 plus L2 over C, and then that's just V squared over 2C squared. Simplifies it quite a bit. The 2's drop out, and this becomes L1 plus L2 V squared all over C cubed. So there's how much difference I should have in moving at 90 degrees right there. But what I'd like to do is, this is a difference in time. I'd like to get at a difference in distance, how far the light traveled. And since we know light travels at the speed of light right here, delta d right here, the change in distance should just be c times the change in time. There's my change in time right here, which is all of this right here, which is L1 plus L2 all over c cubed times v squared, which is, I'll cancel a c, so this is just L1 plus L2 times v squared all over c squared, right there. So there's how much difference in distance that this one moved and that one moved right here. Now, when you notice right here, if one wave is like this, these are the light waves, and the other one, let's just say the other one is shifted a little bit, if this distance for this other one, if it shifts by a whole wavelength, that is, if this moves all the way to here, it's right back on top of itself again. If it shifts one wavelength right here. So what we can do is if we want to know how many wavelengths it shifts, we can just divide it by its wavelength, because if it shifts by one wavelength, it's shifted by one right here. So I'm going to call this a fractional shift. Fractional shift. Fractional shift. It's just going to be defined, I'll give it this letter F right here, and it's just the change in distance over the wavelength. It tells me how many wavelengths the distance shifted by. Well, if I just put in my delta D, which is right here, it just adds a wavelength here. So this is L1 plus L2 V squared all over the wavelength times c squared. Okay, now we wanted to know is how much did it shift right here. We already said due to the Earth going around the sun, this term right here, this term v squared over c squared, we said was 10 to the minus 8 over there. Remember, we said that one. So this F becomes L1 plus L2. All of that term is 10 to the minus 8 right there, divided by the wavelength. And we said the wavelength of the light was 500 times 10 to the minus 9 meters. Everything's in meters right here. Okay, so what does that give me? Well, 10 to the minus 8, 10 to the minus 9, if I bring that up here, that's just 10 to the 1. So that just gives me 10 to the 1 right there. And then we can get rid of a 0. So this is really just L1 plus L2 all over 50. 50 right there. Now, Michelson wanted to keep improving on his experiment. How did he do that? Well, he did it by increasing these lengths right here. He got these lengths up to around, not exactly equal, about 11 meters, which is pretty long, but he did it with mirrors and light going back and forth many times. And this one, 11 meters right here. So that means our lengths are 11 meters. Well, 11 plus another 11, that's 22 over 50. That's about half, a little bit less than half, 0.4 something, 0.44 say. So what he says is if your lines are like this, and then you rotate it 90 degrees, this, from shifting from here to here would be a 1, shifting from here to about halfway, these would shift 0.44 all the way across. He'd easily see that right here. Matter of fact, he said I could see it even if it shifted by 0.01 right here. So he says I could see a shift of 0.01. And I can't see it, and there should be at least a shift that much, right, in 0.44. I can't find it. He tried every possible combination, doing it different times of the year, doing it the Earth's rotation, never seemed to see this shift right here. It bugged him completely right there, even though he was the first American to win the Nobel Prize, because it was a null result right here. He wanted to find it right here. Well, what does that mean right here? Well, that means one of two things. It means that, well, maybe the ether frame goes around the Earth just like the Earth goes, maybe moves like the Earth around the sun. That would be kind of strange if still space seemed to follow the Earth's motion. I doubt that. Another thing is they thought maybe it's like we have friction around the surface of the Earth and we're dragging it along with us. It's like dropping a tennis ball through some molasses. The molasses near the tennis ball stays kind of close to it right here. And maybe it's called ether drag. Maybe we're just dragging it along with us. But they finally figured it can't be that, because when you're looking at a star through a telescope, let's say there's a star right above you and here's a telescope right here. And the Earth is moving this way with a velocity v. We know the Earth is moving just around the sun. If you shine the telescope up right ahead, well, as the telescope moves this way, the light's going to kind of hit this end side of the telescope. So what you have to do to your telescope, you have to tilt it just a tiny bit this way, right here. And as you go around the sun, you've got to keep changing your tilt. And so if you follow that, it seems to follow like a little circle in the sky right there. And the diameter of that circle, very small. It's like in the order of arc seconds, which is thousandth of degrees. That's why you don't notice it right here. Now, if we were to pull along the ether rate along with us, this wouldn't happen right here. The light would just keep going straight right here because we weren't moving relative to still space. So that it's not dragging us along right here. It actually took Einstein to figure this whole thing out right here, and he did it without this experiment. He says, I never saw this experiment right here. But he worked it all out, figured it out, and we'll probably just go through that next time right here. Well, how did he figure this thing out without this? He just came over to here and just with pure logic. Einstein was a bright guy. They didn't call him Einstein for nothing right here. So so next time we'll go through how Einstein figured this whole thing out right here. Okay.